Poor visibility is one of the major causes of delays in aviation today. Present methods of tracking aircraft on the ground rely on visual means. This video offers a solution to this problem. Controlling aircraft on the ground when visibility is poor often results in delays. One major U.S. airline estimates that these delays increase their operating costs by $150 million per year. The problem of tracking aircraft on the ground could be addressed in a number of ways. For the first time, however, we present a solution which requires no new equipment to be installed aboard the aircraft. The live system provides ATC with a label giving position, identification, and other information, for instance, type and gate or runway. The live system also provides labels for ground vehicles on the movement area. The benefits of this are improved ability to prevent unnecessary runway incursions and enhanced airport capacity, particularly under poor visibility conditions. The live system uses a number of sensor stations installed alongside the runways and taxiways. The system utilizes existing standard SSR interrogations for surveillance. By transmitting the interrogation pulses P1 and P3 from two different locations, virtual surveillance sensors are created which have a confined area of coverage shown as footprints. This overcomes the garbling problems which conventionally beset ground radars. By sweeping the interrogation in a controlled sequence over all of these virtual sensors, the entire movement area of even the largest airport can be covered in a period of 1 second. The live system is based on the Mode A interrogation of SSR transponders. These are already carried by almost all of the world's civil aircraft. To prevent responses on existing local radars, the live system mutes the transponders on the ground. The SSR muting signal is transmitted from all stations which are outside the footprint of the virtual sensor currently being interrogated. The muting signal consists of pulse pairs P1 and P2, which activate the SSR side lobe suppression. These transmissions are repeated at a high repetition rate. One of the unique features of the live system is that the muting signal is effective at ground level. However, its vertical coverage is limited to an altitude of considerably less than 1,000 feet. At the request of FAA, the principal characteristics of the live system were measured at the Maastricht-Aachen Airport in the Netherlands. In order to realize these measurements, live system transmitter stations were installed alongside the taxiway. Distance markers indicating the distance to the center of the sensor were installed in order to enable the dimensions of the sensor footprint to be established. An SSR receiver was installed. Caravans were used as observation posts.
Kilo, you may see a helicopter doing test runs on taxiway 1 and 2, staying clear of the runway at all times. Roger, Kilo.
The first test carried out was the determination of the area of coverage of the surveillance mode. The receiver signal is displayed on an A-scope, triggered by the transmitter pulse. This ensures that the responses to the live system interrogations are synchronous. Traffic is observed as it passes the area of coverage of the live stations. At each of the beginning and end of the aircraft response, the distance of the aircraft to the center of the sensor is noted down. The averages for over 250 passes of aircraft on the runway were 170 and 105 meters. For the taxiway, the averages were 56, and 101 meters. The root mean square was calculated for the deviations from the averages. The same area was used for measurements of the muting signal. To measure the horizontal coverage of the muting signal, 4 live system stations were used. The 2 outer stations transmitted P1 and P3 interrogations. The 2 inner stations transmitted high PRF muting signals. A test transponder was moved along the line through the muting stations. The average distance from the muting stations at which the test transponder responded was approximately 100 meters. During the measurement of the vertical coverage of the muting function, 4 stations transmitted muting signals, thus providing an effective muting coverage over a lane of approximately 1/4 of a nautical mile in length. A helicopter flew directly over the muting stations at successive altitudes of 100 feet, 200 feet, and so on, until it was detected once more by the local radar. The same procedure was repeated at a lateral separation of 75 meters from the stations. On the radar screen, the circle shows the area over which all video of the local radar is blanked. The orange line indicates the border of coverage of the muting signal. The dashed line represents the approximate flight pattern of the helicopter. We will now closely follow the results of the flight trial. The helicopter is approaching the test area at 300 feet. Hit. Hit. Miss. Hit. 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 Miss. Hit. 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 The probability of detection on this stretch was 82%. These trials were witnessed by experts from aviation authorities, organizations, and manufacturers from around the world. The trials have demonstrated that transmitting P1 and P3 from different locations is an effective way of limiting the area of coverage of a live sensor. Solid coverage of the muting function was achieved on the ground, and muting effects can be limited to an altitude of 300 feet. These tests demonstrate the feasibility of the live system. The benefits of the live system are improved ability to prevent runway incursions and enhanced airport capacity, particularly under poor visibility conditions. The benefits of the live system are achievable without the need for new airborne equipment, with minimal installation impact, and with available technology.